Thanks for the very kind introduction, Raphael. So today I would like to answer the questions why digitalization plays a major role for sustainability in the circular economy, how we approach that topic, and what can be done. So some examples where it can kick in. May I ask a question in the beginning? Who of you is chemist or has a natural science background? Business? Digitalization? All of them? So you see, very few people have that combined know-how. And that's, I think, very important, at least to understand each other's language. So before getting started, you already mentioned that I have different roles in Bayreuth. So one of the roles, I'm heading the Department of Polymer Engineering, a chair at the university with about 40 people. But I'm also CEO of the company New Materials Bayreuth with about 60 people. Both research-driven, and sustainability plays a quite important role here. An important one is that we organize ourselves in material classes, also including metals, by the way. But digitalization and sustainability, circular economy are across the different materials, because often in applications you have multi-materials. And that's why it's needed to have that general overview. Yeah, and we are not doing research just for doing research, but we are committed to application. So we are interested always to apply it later on so that our customers, our partners can earn money. But now let's step into the topic of sustainability and circular economy. So what are the drivers? And I think all of you are aware of it. A very strong driver is regulation. So there are different regulations, directives in place or get into place, which demand for a certain share of the recycled product, for an extended product responsibility, for design for recycling, and so on and so on. Without regulation, we would perhaps not discuss so intensely about the topic of circular economy. But there's also other drivers. The first one is quality. Can we effort to reduce the quality? No, we can't. So it should be at the same quality as before. But we all know that when you're recycling a material several times, due to degradation, the material properties might decline. And the other one is, for sure, the most important material characteristic, costs. Ideally, you would have at a certain quality, virgin material quality, the identical costs. Due to scarcity in the market, often we see that recycled material is more expensive than virgin material if it's good quality. And that is also an issue which demands for solutions. So summing it up, it's basically a triangle of conflicting interests: quality, costs, and sustainability. Digitalization can help here to overcome these conflicts and to guide the way to a cost-efficient, high quality, but also sustainable future. Mentioning one topic here, a similarity check. We have an additive manufacturing plant where also circular economy plays a quite important role. So it's a kind of playground for understanding what is going on a larger scale. What do you do in additive manufacturing? Basically, you have different steps. So the upper left corner, that's the printing stage. And after the selective laser sintering, you have to unpack the material. You have to get rid of the powder, which is all around, in order to finally clean up the material. 80% of the material is still powder. It has been processed once. It has changed its characteristics, similar to recycled material. And the question is here, how much material can you feed back in order to be cost efficient at adequate quality? So here you see some examples. That's the powder sintering stage, and then it enters all the additional steps. If you check what is important, what is the goal here? Minimum powder or material waste, low material prices, reproducible quality, constant processing parameters, so there's a lot of similarities in. And if you check the complete cycle, you see that after the process, you need to depowder, you remove the parts, you get the residual powder, you refresh it, so you add some additional fresh powder. Some of the material can't be used anymore, so it has to be discarded in order to finally end up in the circle again to get new feedstock. So if you would map a similar picture for plastics recycling, it would be identical. So here at a small scale, we can learn what it takes in order to manage that process. We have heard before that data is a quite important one here. It's both offline but also inline data. And here you see an example of all the elements you need to measure in order to steer that laser sintering process correctly. Let's now switch back to the topic of circular economy of plastics in general and how digital and circular can team up and build a strong team. Getting back to the topic of data generation first. What do we need? We do need process data, extrusion, compounding, temperatures, blah, 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 you name it. Material information, and we will have a follow-up talk of Andreas Wolny from BASF together with Bennett Brenken from Reifenhäuser on the topic digital product passes. It's offline analytics, DSC, GPC, and so on and so on. So we heard a talk of Nech this morning. And it's inline and online data. Inline and online data is particularly interesting because it allows you to at line and in real time control processes and analyze quality. Here is an excerpt of what kind of technologies are available, for what they are used, what the limitations are today, and last column, you see that there's a lot of machine learning techniques already present. So you use machine learning in order to make these inline data manageable, but also get the most out of it. Just the first example here, inline Raman spectroscopy, available, very fast. What can you do? You can do chemometry, so you can analyze the composition of materials. And based on that one, you might also detect additives, and you can calculate inline a melt flow index. So that's something which is quite of value if you have it. And here you see just the experimental and the predicted data. So let's now review that picture of cost, quality, and sustainability, and let's check what we can do along the line. Because what we have not talked about yet is that there's not the one recycling path, which is absolutely clear which one to take, but there are different ones. You may use mechanical recycling via recompounding, repalletizing the material, or using solvent-based processes. You might use chemical recycling, getting back to monomers, or getting back to naphtha and gas. But the question is, when to take what? And you also see there are different steps involved, from the collection, separation, to the pre-treatment, to the individual mechanical and chemical processes. So different pathways. I've seen in many studies that you basically do it at one step only. You optimize one individual step. So you can do that, for instance, for sorting. You use sensing technology in order to assess the characteristics of the material. For example, here you have textiles, mixed textiles. You use near-infrared spectroscopy in order to sort the material in a very accurate manner. So it's a very elegant process, works pretty fine. The next one, where also sorting is the challenge or the task, is using fluorescence to sort black plastics. So often, black plastics are very difficult to distinguish in terms of the chemical composition, and fluorescence spectroscopy here can identify the individual materials in order to make the sorting as good as possible. You also see these different layers in between. That's a neural network, which basically helps you to separate the problem and to extract the main features. It's not only available for sorting, but also at other stages along the line. One other stage, which you use for chemical recycling, is pyrolysis, to get back to an oily substance. And just around the corner, you see some examples. And here the question is, how do I get most yield out of that pyrolysis? Particularly when you have mixtures of materials like PET and polyamide 6, which often happen in true applications. So here again, you're using a neural network in order to get a max of the output based on the processing parameters which you change. And the same is true also for other compositions. So for instance, when you have PET, polypropylene, and HDPE, also typical materials for packaging. So if you want to pyrolyze these materials, it's also very good to know where you can have the maximum yield in these different compositions. So if you look to the right sides, here you see a triangle of the different compositions, and the max yield you can always have if you have a very high content of polypropylene and you can effort a certain content of the PET inside the mixture. All that cannot be done, or at least I can't do that with my human brain, because there might be 100 different parameters influencing that process. You may optimize a process when you have one influencing parameter or two or three, but with hundreds, impossible to think about it. So here, machine learning is a very elegant technique. Let's now switch to two project examples we are currently running at my facilities in Bayreuth. The first one is about AI-assisted reactive mechanical recycling of PET. So what's the problem with PET? PET is very well known to be strongly available from mechanical recycling. Nevertheless, if you think about the different PET grades available, you have fibers, you have bottles, you have bags, and so on and so on. And all these materials have a different intrinsic viscosity, molecular weight, different characteristics. Often they end up in the same bin. And that's a topic. Besides, you have also from batch to batch variations. In the end, you would always like to have a constant quality again. So you have different mixtures, but whatever you do, you have to prepare a recipe which gives you constant quality. So how can you do that? Often when processing materials to break down the chains, you reduce molecular weight, the viscosity and the mechanical properties, but you can increase the properties again via using chain extenders like Jonquil. And that's what we are doing here in our project. We are targeting the problem not input driven, but we are reversing it. So we define first what kind of material we want to have in terms of quality, and we steer the process, the processing conditions, the content of chain extenders, the input sources, so that we can end up with the same quality always. Again, the target is here to have always constant quality. So if you have a desired property, we do the experiments AI driven in order to see what's the best way to get there. Here I have to make a small comment because we had heard before, big data is very important. It is the essence, the fuel of machine learning. That's not always true. You can always leverage the value of small data. And one example I show you exactly in that case here. So what's the value of small data? Here you can use the process of Bayesian optimization. So you will become some AI experts after the end of the talk. Bayesian optimization is a pretty straightforward technology. What do you do here? You select 5 random experiments with different processing parameters, these different P's. You perform the experiments, you measure your target property, which could be intrinsic viscosity, which could be a glass transition temperature, whatever. Based on these very few experiments, you train a model. It will not be a good one, but it's a good starting point. Subsequently, you perform virtual experiments. So based on your poor model, you calculate 10 to the power 6 different variations of these processing parameters. So you predict also the properties which you assume with a certain uncertainty. You evaluate which result, which trial you have not taken yet, gives you the maximum output, making your model better or optimizing your properties. You do the next experiment with a selected set of parameters. You perform the experiment and you loop until you end up with the desired quality of the data or with a high accuracy of the prediction model. Okay? So that's what you do also by intuition. So if you're standing in a lab, you're doing experiments, you learn from the experiments, you think what could happen next, and then you do the next experiment. And this one is machine learning driven. An example here, and again, it's about rPET, reactive extrusion. We are doing that on a tandem line, so combining two extruders, a lot of different parameters, about 60 to 70 processing and material parameters. And that's what we've been doing. The first 5 dots are, these reddish dots are the random experiments. And you already see the average, the highest so far, was relatively low, and we wanted to increase the viscosity. So let's see what happened with Bayesian optimization. 5 more trials, and we've been tripling the viscosity we gained so far. So that's the value, from my point of view, the value of small data. You can start small in order to, for instance, optimize your processes or optimize your formulations. Let's now get to a second example, the project SpecRack, which deals with the inline spectroscopy for real-time control of recycling. Here we are leveraging the value of Raman spectroscopy. So again, what's the challenge here? So it's quantum technologies. Raman spectroscopy is a quantum technology, and here we are trying to optimize for high efficiency the mechanical recycling process in order to have highest quality. You also see it's not us alone, but it's a really huge project. Ourselves, the University of Jena, Techno-Compounders recycling company, Andres and Hauser as the one doing the Raman spectroscopy, and BASF. So what's the challenge often? First challenge, molecular weight. So you degrade the material, reduce the molecular weight, but it's very challenging to measure beforehand. So can Raman spectroscopy measure the molecular weight of the material plus its composition in line? The second one is, often you have polymer mixtures or contaminations in the material. You can take action and add compatibilizers if needed, but you would only do that to a certain level and if really needed. So here again, it's about chemometry, so to measure what's the composition of the product in order to finally end up with steering the process. So here is a schematic overview of what we are doing. So on the left side, you see a schematic picture how Raman is working, but that's not for today. On the right side, you see that we are measuring Raman both at the beginning, before entering the extrusion, online, and after the extrusion. So we can measure what happens during these individual steps. We are also measuring inline viscosity in order to see how to correlate it, and we are doing a lot of offline analytics to get that combined picture. And that will be used in order to not only control the process, but to autonomously run the process in the end. So you just feed in your recycled material, you know what the composition is, you know your target, and the process is steering itself. Okay? So as mentioned, quite strong partners. One important element here is to create a database for Raman. So we are artificially contaminating the material in order to have a certain library of compositions, and then we are doing all the experiments, and we are also optimizing the Raman spectroscopy, the measurement technique itself. And we are using different case studies. It's on the polyolefins and the polystyrene and the styrenics and so on and so on. So there would be different materials included. So finally, 5 minutes left. We have seen that it makes sense to control the individual stages of a recycling process, but it's also important to keep the overall thing in mind. So if you optimize, for instance, a washing process, perhaps that's not needed because the properties will anyway not be influenced. Or it does make sense to invest a little more energy, and often energy is also costs, in order to make a higher quality product. So what we've been setting up at the facility in Bayreuth is for the mechanical recycling a full loop. Oops, sorry, one back. A full loop starting from shredding the material to pre-treating, washing the material, to the mechanical recycling, to deodorization. And some elements I will show you here. One element in particular, when you have very fluffy material, fleeces, foams, and so on, they're difficult to dose, difficult to handle, and difficult to transport. So what you can do is using a pallet press, from Carl in this case, in order to compact it and to make palletized materials. So that's one part. And yes, example you can see here. So for PET fibers and for EPP foams, you see how you can compact the material from very low densities, 30 and 40, to 300 and 600 bulk densities. So very efficient. Yeah. The second one is a washing line. So it's not a washing machine, but it's really, as you see, a pilot plant where we can do washing of the material, hot washing, cold washing, drying the material again. But the particular And most important step we are doing here is shown here. So it's a friction washer. So the material enters a very small gap, and you can efficiently clean up the material and even remove metallized parts and films or coatings from the material. So it's not only washing, but it's also unlayering material. Very efficient in terms of energy. So we've been running that now for several months, and you see that you have savings in terms of energy between 70 and 90% compared to conventional washing technology. Yeah, if you have the pellets, then you need to recompound. So I think that's a well-known step. You do twin screw extrusion in order to recompound the material to get pellets again, or also to filter out materials with different meshes. And finally, odor is a topic in the industry, we just heard before. So these smell detectors, but how to remove smell, either already in washing or during the compounding step, or afterwards in a small silo here. So you bring hot air through the silo in order to remove the odor. We have combined all these steps. All data along the chain is digitally available so that we can assemble all the information all along the lines in order to really get the most out of it, to control the process in terms of what quality we need, at which costs, and at which carbon footprint. As a final slide, I have a teaser for you. So some of you might be interested in participating in projects, and we are just running an initiative which will be submitted end of this month on recycling of coated materials, for instance for bumpers. So if you want to become member of the advisory board of these projects, please do so. Please reach out to us. It's at very low costs because it's only a working day of you or supplying some materials or whatever, so it's not a really big step you have to take, but it's a small contribution and you become part of the project and you also get the materials shared. So if you're interested, reach out to us in order to be part. Yeah, finally, key takeaways. It should have become clear that we have that conflicting interests of costs, quality, and sustainability measured in quite different KPIs. So it's euro per ton, it's a stable quality and tracing of the material, and it's the carbon footprint and the recycling rate. But via digitalization, you can overcome these conflicts. For instance, by sorting the material in an efficient manner, which helps you in terms of the quality. You may also use new technologies and reduce the energy input into these different processes. So that helps you to reduce the carbon footprint, to make it also not only advantageous in terms of the regulation, but also in terms of the carbon footprint of the material, because you don't want to invest more carbon than with a virgin material. And finally, also the topic between quality and sustainability. Having a constant quality is a quite important one, and this goes in hand also with the digital product passes, which we will hear on in the next lecture. So thank you for your attention. That's part of my group. So we are conducting once a year a seminar. That's not Bayreuth, but it's the Austrian Alps. And my heart is really close to sustainability and digitalization. We have also been starting a new master program on digitalization and sustainability in materials in Bayreuth, and a research training group on copolymer informatics. So we are dedicated to that one, also for training and preparing the next generation of students and graduates for the industry. Thank you for your attention, and open to questions.
Holger, thank you so much. Are there questions from the audience?